In the last lecture, we have talked about independence and we define independence as A and B are said to be independent events if probability of A intersection B can be written as probability of A into probability of B. And then we have discussed some properties of independence. Okay, so a natural question now comes into the mind is that, well, we have talked about the independence of two events. Is that definition can be extendable for more than two events? Can we talk about the independence when we have more than two events? So this is a natural question, and that was what we are going to discuss now. And when we are going to talk about independence for more than two events, there are concept of two kind of independence. One is called pairwise independent, and another thing is called either only independent or mutually independent. Okay, so we are going to talk about these two concepts now, these two kind of independence now when I have more than two events. Well, so what is pairwise independence? From the name, it is very clear that the pairwise independence basically means that, well, if I have a at most countable collection of events, E1, E2, so on, and we will say that this collection of event is pairwise independent, if I take any two events from this collection, then that two events will be independent. So that basically means that if I take EI and EJ, then probability of EI intersection EJ will be equals to probability of EI into probability of EJ for all I not equals to J. So if I take any two events, any pair of events from this collection, it will turns out to be independent. Okay. So that means basically, right? So that means basically pairwise independent. Pairwise independence. So that basically means that, well, I have a sequence of events E1, E2, so on. This is the at most countable collection of events. This is at most countable collection of events. And we say that this at most countable collection of events is pairwise independent if probability of EI intersection EJ, that quantity turns out to be probability of EI multiplied by probability of EJ for I not equals to J. So I take any pair from here, that will turns out to be independent, then it is pairwise independent. Okay. Next concept comes is basically independence or mutual independence. Independent or mutual independence. So when we are going to talk about independent or mutual independence, we have to basically first think of a finite collection of events. We are going to define the mutual independent or independent for a sequence of finite collection of events. And once we can do this one, we will extend this one for a uncountable, for a countable collection of events, as not countable collection of events. Okay. So first we are going to define it for a finite collection of events, and then we are going to extend it for a countable collection of events. That will be the way. Okay. So what does this? What is the meaning of the independent in case of a finite collection of events? The meaning is that if I take any sub collection of events from E1 to En, which I have denoted by En1, En2 up to Enk, if I take any sub collection of the form this, then P of intersection of Enk equals to product of P of Eni. Okay, I am coming into the this thing. I am coming into that this will be I, this k will be I here, this k will be I here. I am coming into the example, so better to try to understand it with one example. Suppose for simplicity, suppose I take n equals to 3. Okay, suppose I take n equals to 3, and let us check what are the conditions I need to check in case of n equals to 3. So if you have n equals to 3, so what are the conditions I need to check here? Okay, let's take n equals to 3. So that means I have a collection E1, E2 and E3. So now what the definition says? The definition says that if I take any subcollection, then I can write the probability of the intersection of the events is same as the product of the probabilities. Okay. So what does this mean? In case of the three events, it basically means that, well, uh, I can take, what are the subcollection I can take from here? I can take the subcollection E1, E2. I can take subcollection E1, E3, E1, sorry, E2, E3, and finally E1, E2, E3. Okay, these four subcollections are possible in this case. So in this case, I need to check that if probability of E1 intersection E2 is equals to probability of E1 into probability E2 or not. If this thing is true or not, I need to check if E1 intersection E3 is equals to probability of E1 into probability E3, whether this thing is true or not. I need to check if probability of E2 intersection E3 is same as probability of E2 into probability E3, if this equality is true or not. And finally I need to check if E1 intersection E2 intersection E3, whether this quantity is same as probability of E1 into probability of E2 into probability of E3. Okay. So if I have to check whether three events are independent or not, I need to check these four conditions, and if these four conditions hold true, we say that the events E1, E2, E3 are mutually independent. Okay. Note that in case of the pairwise independence, if I want to check, if I want to check if E1, E2 and E3 are pairwise independent or not, pairwise independent or not, then we then I need to check conditions 1, 2, 3, where this one is 1, this one is 2, and this one is 3. And maybe I call this one is 4. So to check if E1, E2, E3 are pairwise independent or not, I have to take any two from this collection E1, E2, E3, and I need to check whether the probability of the intersection can be written as the product of the probability. So that basically means that I need to check 1, 2, and 3, but when I have to check whether three events are mutually independent or not, I have to check another extra condition, which is basically probability of E1 intersection E2 intersection E3, whether this probability is equals to the product of the probabilities or not. Okay, so I hope this pairwise independent and mutual independent in case of the finite collection of events is clear with everyone. Okay, so you see that it is very very clear now from here is that, well, if I have to check, so that basically means that, well, I come to this point later. Before that, maybe we talk about how we can, when we say that a countable collection of events are mutually independent or not. So we will say that a countable collection of events E1, E2, so on are mutually independent or independent if any finite subcollection are independent. So I will take any finite subcollection from the countable collection, and then I need to check that whether that subcollection is independent or not. That means basically I need to check that whether this condition for any value of k, whether this condition is true or not, where k lies between 2, 3, 4, 5 up to n. Okay, clear? So that basically means, well, pairwise independence, we have no problem defining whether it is a finite collection of events or whether it is a countable collection of events. It is not a problem. I have to take any two and I have to check that whether any pair of events is independent or not. If they are independent, any pair is independent, we say it is a pairwise independent. If not, it is not a pair. It is not pairwise. Note that if there exists just one, there exists only one pair for which the independence is not there, then we will say that the collection is not pairwise independent. Now, the complete independence or mutual independence or independence, we first define it for the finite collection of events, and for the finite collection of events, it is defined by saying that, well, if I take any sub collection of events from the finite collection of events u1 to n, then if I can write that probability of the intersection of all the events in the sub collection is same as product of the probabilities, then we say that the finite collection of events u1 to n are independent. Now we extend it for the countable collection of events. For the countable collection of events, E1, E2 dot 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 are said to be independent if any finite subcollection are independent. Okay, clear? So let us see some of the remarks on the independence. Well, the first remarks partially we already talked about that. Well, if I have three events, if I have n equals to 3, that is 3 events, then to check whether the 3 events are independent or not, I need to check the 4 conditions. And you see that from here, we can easily understand that, well, in if we have n events, and if we want to check if they are pairwise independent or not, independent or not, then we need to check how many conditions we need to check. So for n events, I have to take any pair and I have to check basically whether they are independent or not. So we need to check NC2 conditions. But when I need to check, if I need to check if they are mutually independent or not, if we need to check if they are independent or not, we need to check how many conditions we need to check. We need to check basically 2 to the power n minus 1 conditions. And you can understand from where this quantity came. This quantity came because 2 to the power n came because it is basically nothing but summation. Basically, this quantity is same as summation NCI. I runs from 2 to n. So 2 at a time, 3 at a time, 4 at a time, up to n at a time. I will take and I'll check whether the probability of the intersection can be written as the product of the probabilities or not. And this summation is exactly equals to 2 to the power n minus 1. So this is the idea. So that basically means to verify the independence of n events, I need to check 2 to the power n minus 1 conditions, and to verify if this collection is pairwise independent or not, I need to check NC2 conditions. And note that these NC2 conditions are basically part of 2 to the power n minus 1 conditions. Okay, so that implies that independence implies pairwise independence, because you can understand that when I have to check independence, I actually check whether they are pairwise independent or not, because two at a time actually give me the pairwise independence. Natural question is that whether the reverse is true, whether pairwise independence implies independence or not, and the answer to this one is that in general it is not true. And one of the example is given here, and this example is very simple example. So what I am doing is that I am tossing a fair coin two times. So if I toss a fair coin two times, the sample space is basically this, that head tail head, or tail tail. Now let us consider three events, E1, E2, E3. What is E1? E1 is nothing but the event that the first toss result in a head. E2, second toss result in a head. And E3, both the toss have same outcome. Okay, both the toss have same outcome. Now, in this case, what we are going to check is that whether these E1, E2, E3 are pairwise independent or not, and then we are going to check that whether E1, E2, E3 are independent or not. So that once I check whether E1, E2, E3 are pairwise independent or not, and suppose we can show that they are pairwise independent, then we need to check this condition only to check if they are independent or not. Okay, let us check one by one. So, so the scenario is as follows. Example: the sample space is head, head, tail, and tail. We have taken equally likely case. So P of head is same as P of head is same as P of tail is same as P of tail, and which is same as 1 by 4, because sum has to be 1. Well, now we consider E1, which is basically the first outcome is head, and it is clear that probability of E1 is half. Then E2, which is the second one is head, so that means that P of E2 is also half. And third event E3 is both the outcomes are same, so in this case also probability is half. Okay, now let us talk about what is the probability of E1 intersection E2. I want to check whether they are pairwise, E1, E2, E3 are pairwise independent or not. So I need to find out this probability, and this probability is basically, you see that the intersection of E1 and E2 is only the singleton set head. So in this case, this probability is 1 by 4, and which is exactly half into half, which is probability of E1 into probability of E2. And in the same manner, it is very easy to check that, well, probability of E1 intersection E3 is same as probability of E1 into probability of E3, and probability of E2 intersection E3 also same as probability of E2 into probability of E3. So that means that E1, E2, E3, so this implies E1, E2 and E3 are pairwise independent. Okay, so in this case, E1, E2, E3 are pairwise independent. Now, suppose now I want to check that if E1, E2, E3 are mutually independent or not, or independent or not. So what I have to do, I have to check the condition whether probability of E1 intersection E2 intersection E3 is same as probability of E1 multiplied by probability of E2 multiplied by probability of E3 or not. And in this case, you can check that probability of E1 intersection E2 intersection E3, which is basically probability of head-head. Only this point is common in all the three sets E1, E2, E3. So that basically means that this probability is 1 by 4, which is not equals to half into half into half, which is probability of E1 into probability of E2 into probability of E3. Okay? So that means that in this case, this implies that in this case, E1, E2, and E3 are not independent. Are not independent. Yeah? So that means this example shows that in general we cannot tell that pairwise independence implies independence. Okay. Next example, which is again a very interesting example. Well, for three sets, we can think that if I check this condition, does that mean they are independent? If I check this condition only, does that mean they are independent? And the answer to this one is no. And this is one of the example of that. See that in this case, I take S is of this form. This is nothing but if I throw a die two times, this is the sample space corresponding to that random experiment. So I have 36 points. I take all the elementary events are equally likely. That means the probability of each outcome, each elementary outcome is 1 by 36. And we define three events E1, E2, E3 like E1 is first roll is 1, 2 or 3. E2 is first roll is 3, 4 and 5. Note that 3 is common in both the case. And third is E3 sum of the rows is 9. And you can check, I am not going into the checking because this is checking is very simple. You can check that in this case, this condition that probability of E1 intersection E2 intersection E3 turns out to be probability of E1 into probability of E2 into probability of E3. So this condition will going to hold true for this example, but in this example, this E1, E2, E3 are not pairwise independent. So even if I take the last condition, that does not mean that they will be independent. So this condition does not even mean that E1, E2, E3 are pairwise independent. So my point is that, well, if I have to check whether the events are independent or not, I have to check all the 2 to the power n minus 1 conditions. There is no way to escape. Okay, fine. So that is about independence. Next concept we are going to see is the conditional independence. So conditional independence again is straightforward extension from the independence. So we have seen that for the independence we defined independence as follows, that well A and B, two events A and B are independent if and only if, this is the definition, that probability of A intersection B equals to probability of A into probability of B. The conditional independence A and B, or I should write in this manner, that given a event C with probability of C is strictly greater than 0, with probability of C is strictly greater than 0, the events A and B are said to be conditional independent if, well, in this case I have A intersection B equals to probability of A into probability of B. That will be probability of A intersection B given C is equals to probability of A given C into probability of B given C. So there are three probabilities involved in case of the independence. So all these three probabilities turns out to be the conditional independence. Okay, and now you can think of pairwise conditional independence. So given C, A1, A2, A3 are said to be pairwise independent if you take any pair from AI. that will be conditional independent. Okay, and you can talk about the mutual independent in the same manner. So once we define the conditional independence for two events, that can be extended for pairwise independent and mutual independent. That is not a problem. Okay, now a question comes into the mind that, well, if A and B are conditionally independent given C, does that imply A and B are independent? By A and B are independent, I am talking about they are unconditionally independent. So the question is that if A and B are conditionally independent given the event C, does that imply A and B are unconditionally independent? And this is one of the example which shows that, well, in this case, A and B are conditionally independent given C, but A and B are not independent. And this example again is very simple. I left it for your exercise because taking that they are conditionally independent and they are independent is quite simple. Just write it down to the very simple example, and I left it as an exercise. Well, with that, I stop in this lecture. Next lecture, we are going to see random variables.